This is Chapter 9, Cryptography, Part 2. First, we'll talk about keys and key management. Keys, key space, and key management. Of course, the key is a value that is input to a crypto system, and it needs to be unique. A key space is the set of all possible keys. An example of a key space is how large is the key space for a briefcase lock with two 3-digit lock combinations? Combinations run from 000 and 000 all the way to 999,999. So there are 1 million keys in the key space. Does this mean a thief would have to try all 1 million combinations? No. A thief could get incredibly lucky and guess the correct combination on the first try or relatively early in the process. However, on an average, an attacker will guess the correct combination halfway through searching the key space. But does this mean the attacker would have to try on average 500,000 combinations? If each attempt took 2 seconds and the attacker worked nonstop day and night, this would need 11 days to open the briefcase. However, the actual resistance to this brute force attack is closer to 17 minutes. Why? It has to do with a weakness in the briefcase algorithm. Because there are two separate locks with 1,000 combinations each, on average it takes 500 attempts to guess each sub combination. So all you have to do first is find the left combination. Then the attacker will need only to try 1,000 plus 1,000, only 2,000 maximum combinations. And if you hit the left combination early on, let's say it's 142 or something, now you've saved a lot of time and you could just start working on the right-hand side. On the average, the attacker would need to try only 1,000. At 2 seconds each, that's 16 minutes, 40 seconds. This shows why increased key space, or even an increase in the number of bits in a key, doesn't necessarily provide much more security, but it does provide more security than a smaller key space. If a briefcase maker wanted to sell you a product with 6 key with 6 3-digit locks, would you buy it? Think about that. Key management, of course, is one of the most difficult and critical parts of a crypto system because it asks how often are keys reused. Key distribution techniques: paper, hardware, digital media. Paper distribution requires no technology to use. However, it does require a person to do something to install the key. This human role can introduce errors or give a disgruntled person a chance to compromise the system. Digital distribution can be in the form of CDs or email. Note that you must protect the keys in transit. Some form of secure transmission must be used. For physical media, tamper-proof cases and registered mail give some level of assurance. For electronic distribution, a higher level key, known as a key encrypting key, must protect the keys in transit and storage. This, of course, requires that you first distribute the key encrypting key by some alternate secure mechanism. You should use key encrypting keys only to encrypt other keys, not data. Excessive use of any key could lead to it being compromised. You can distribute a key by way of hardware with a personal computer memory card International Association PCM-CIA card, a smart card, or a plug-in module. The advantage is that you transfer the keys directly from the key transport mechanism into the crypto device without anyone viewing them. No copies exist outside of these components. Key distribution centers. Rather than each organization creating the infrastructure to manage its own keys, a number of hosts could agree to trust a common key distribution center, or KDC. All parties must trust the KDC. With a KDC, each entity requires only one secret key pair between itself and the KDC. Kerberos and ANSI X 9.17 use the concept of a KDC. So let's talk about digital signatures and hash functions. First, we'll talk about hash functions. A checksum, summary information appended to a message to ensure that the values of the message have not changed. Here's a credit card checksum example. Credit cards have a hash digit that validates the card number. The algorithm for calculating this is the LUHN formula based on ANSI X4.13. You follow these 4 steps. 1, starting with the second digit on the right, multiply every other digit by 2. 2, if a result of any doubling is greater than 10, for example, 8 plus 8 equals 16, add the digits of this result. Add all the double digits. 3, add all other digits with the exception of the last digit, the checksum, to this total. And lastly, 4, the difference between the sum and the next multiple of 10 is the check digit. For example, the correct hash digit for credit card number 5012-3456-7890-123X is 6. A hash is like a checksum but operates so that a forged message will not result in the same hash as a legitimate message. It's usually a fixed size, acts as a fingerprint for data. Digital signatures. They bind the identity of an entity to a particular message or piece of information. They ensure the integrity of a message and verify who wrote it. It does require asymmetric key cryptography, where you see the plain text going into the hash algorithm plus a private key equals a digital signature. Now, they actually take the asymmetric encryption methodology and turn it on its head and reverse it. If I encrypt my message with my private key and send it to you, that's my digital signature. You obtain my public key available to anybody and reverse the process. If you can obtain my signature, you know I sent it. And that's also non-repudiation. Can't prove I didn't do it. How a digital signature works. So here you have again the originator sends a message, hashes into a digest where the originator's private key encrypts the digital signature and attaches it to the message and sends it. The message and the digital signature, and the message may not be confidential, but the message and the digital signature go to the receiver. The originator's public key is then applied to the digest, and like I said, it's the original's public key, which you get off the public key repository, is applied to the digest, which then is encrypts, against the hash, and the message is revealed, and you realize what the digital signature is, and that's in fact correct. Cryptographic applications and uses in information system security. Some security product and service categories include anti-malware, forensics, ID management, messaging safeguards, patch management, perimeter defenses, transaction security, digital certificate secure file transfer, and wireless security. Cryptographic applications and uses in information system security. Again, authentication tools include tokens, smart cards, biometric passwords, and password recovery. Access control and authorization includes firewalls, timestamping, single sign-on, identity management, and mobile device security. Assessment auditing tools include vulnerability assessment scanners, penetration testing tools, forensic software, and log analyzers. Cryptographic applications, uses, information systems security, some more. Security management products include tools for enterprise security management, configuration and patch management, and security policy development. Wireless security tools encrypt data to protect them in transit and to limit the access to authorized people. Encryption tools include line encryption, database security products, virtual private networks, the public key infrastructure, PKI, and crypto accelerators. So you ask, where are the public keys stored? They are stored in the public key infrastructure, PKI. It provides user authentication tools that securely send passwords across the internet. PKI is a set of hardware, software, policies, people, and procedures needed to create, manage, distribute, use, store, and revoke digital certificates. Symmetric key standards. The Data Encryption Standard, DES. IBM originally developed DES as what's called the Lucifer algorithm. The NSA modified it and issued it as a national standard in 1977. FIPS publication 46-3 updated its definition. It uses a 56-bit key, which is not very secure, operates on 64-bit blocks of data. The algorithm is better for hardware than used in software. It can rapidly encrypt lots of data. The DES algorithm is in the public domain. It was once state-of-the-art algorithm, but with rapid advances in hardware capabilities and attack methods, Attackers can now crack it in as little as a few keys. It is no longer a secure algorithm. Triple DES, or 3DES, it is a protocol because DES was no longer considered secure. It's a protocol that consists of 3 passes of DES: encrypt, decrypt, encrypt, using multiple keys. It increases the key space from 56 to 112 or 168 bits, depending on whether 2 or 3 keys are used. Triple DES is computationally secure because of the underlying security of the DES algorithm and vastly increased key space. Note that using the same key 3 times produces the same result as single DES. It too is contained in FIPS publication 46-3 and is in the public domain. The International Data Encryption Algorithm, or IDEA. Like DES, this block cipher operates on 64-bit blocks. It uses a 128-bit key. It runs somewhat faster than DES on hardware and software. Ascom Tech AG holds a patent for IDEA, but it is free for non-commercial use. CAST. The CAST algorithm is a substitution permutation algorithm similar to DES. Unlike DES, its authors made its design criteria public. This 64-bit symmetric block cipher can use keys from 40 to 256 bits. RFC 2144 describes CAST 128. RFC 2612 describes CAST 256. Although it is patented, U.S. Patent 5,511,123, its inventors C.M. Adams and S.C. Tavares made it available for free use. Blowfish, a 64-bit block cipher that has a variable key length from 32 to 448 bits. Much faster than DES or IDEA, Blowfish is a strong algorithm that has been included in more than 150 products, as well as version 2.5.47 of the Linux kernel. Its author, Bruce Schneier, placed it in the public domain. Schneier's Twofish was a candidate for the Advanced Encryption Standard. The Advanced Encryption Standard, AES, also known as the Reindahl standard, named for the person who developed it, is a block cipher. Vincent Raymond and Joan Damon, so they get Reindahl, designed AES, and FIPS publication 197 published it as a standard. The AES algorithm can use cryptographic keys of 128, 192, and 256 bits to encrypt and decrypt data in blocks of 128 bits. What you have to understand here is that these keys are actually multiplied against each other using matrix multiplication. 1 round, 2 rounds, and 3 rounds, 128 producing a result, 192 producing a result, 256 producing a result, and you get a result that is like unbreakable. The cipher also can operate on variable block lengths. It is both strong and fast. To this date, it has never been broken. That doesn't mean anything is not unbreakable, but the advanced encryption standard, all these years later, still has not been broken. RC2, variable key size block cipher designed by Ron Rivest. RC stands for Ron's code. RC2 operates as a drop-in replacement for DES and operates on 64-bit blocks. It uses a salt value as part of its encryption routine to make cryptanalysis more difficult. RSA Security owns it. RC4, produced by RSA Security, that's Ron Rivest, Shamir, and Edelman. Secure RSA, that's what it stands for, the 3 authors. RC4 is a variable key size stream cipher with byte-oriented operations. Internet browsers often use RC4 to provide an SSL connection. So let's talk about wireless security. Wireless products have built-in security. The default configuration generally doesn't enable it. They expect customers to enable it, which means if you don't enable it, your wireless access point is not secure. So you really have to enable it when you install a new wireless access point or router on your home network. 802.11 wireless security Wi-Fi provides wireless communications at transmission speeds from 11 megabits per second for 802.11b to over 780 megabits per second for 802.11ac and 100 gigabits per second for 802.11ay. The 802.11 wireless protocols allow encryption through wired equivalent privacy WEP or Wi-Fi protected access WPA. WEP has key management limitations besides being a bitstream cipher. Um, Thus, it is obsolete and should never be used. WPA also is a bitstream cipher, and even though it uses TKIP, the Temporal Key Internet um, Information Protocol, you can't trust WPA as well. It's been broken. You need to enable WPA2, I think it's Temporal Key Integrity Protocol, TKIP. You need to enable WPA2 on your wireless router when you get a new router. Um, you wouldn't be offered WEP in any case. That would not be one of the options, and you probably aren't going to be offered WPA either. But WPA2 is what is required, and that's what you need to enable. Okay, let's talk about asymmetric key and solutions. An asymmetric key solution doesn't require each party to first share a key. The key directory is a trusted repository of all keys, and key escrow is a key storage method that allows some authorized party, third party access to a key under certain circumstances. Key revocation is a concept that you have to understand. It occurs when someone is no longer trusted or allowed to use a crypto system. In a symmetric key system, where everyone shares the same secret, compromising one copy compromises all copies. This doesn't happen in an asymmetric key system. Similar to all employees having the same office key. If a terminated employee refuses to return the key, the organization must change every lock and issue new keys. Thus, it is better, as a matter of consistent policy, to revoke a user's key when he or she leaves the organization. The key directory. If one person is no longer trusted, the directory's manager removes that public key. No one attempting to initiate communications with that person would be allowed to find that key. And then key escrow. Again, such circumstances could include emergency situations when the key owner cannot access a key. Some asymmetric key solutions. The SSL handshake protocol consists of two phases: server authentication and optional client authentication. Digital signatures verify a person's identity or that person's association with a message. And then you need a certificate authority, CA, vouches for the validity of a credential, maintains a list of invalid or revoked certificates in either a certificate revocations list, CRL, or by maintaining the data to support the newer online certificate status protocol, OCSP. Hash functions and digital signatures. Talk about hash function and integrity. Hash functions help detect forgeries. They compute a checksum of a message. They combine the checksum with a cryptographic function so that the result is tamper-proof. A hash is a checksum designed so that no one can forge a message in a way that will result in the same hash as a legitimate message. It's usually a fixed size, resulting in a hash value which is larger than checksum values. There is one very important feature of every hashing algorithm, and if you took IT 2531 with me, you know what that is. That for every algorithm, regardless of the size of the input, one word, one paragraph, an entire book, the output hash value is always the same length. Using MD5, hashing the word one results in this particular hash value. Using MD5, hashing the sentence, "I am a student at Georgia Southern," results in this particular hash value. While they look like they have different lengths. Using a word count, I copy and pasted them into Word and did the count. They are the same length, 120 bits or 32 characters, 32 hexadecimal characters. So actually 32 4-bit hexadecimal characters. So MD5, I don't care if it's one word, one letter, one one punctuation like a comma, or an entire book, it will always produce a 32 character or 128-bit hash result. Now, of course, if you only have 32 characters, there's a very good chance that you're going to have what we call a collision, because at some point, um, a very large topic like a book, or large input like a book, could produce a similar output. There is a chance. That's why we use stronger hashing algorithms that produce outputs of longer lengths. Here are some of them: MD5 message digest algorithm. Again, 32 hex characters. The digest is computationally infeasible to match by finding another input. The secure hash algorithm, SHA-1, produces a 160-bit hash from a message of any arbitrary length. The hash message authentication code, a hash function uses a key to create the hash or message digest. Race Integrity Evaluation Message Digest, RIPEMD, a collection of functions that provide hash values for a wide range of applications. We talk about different algorithms: SHA-1, there's SHA-5, there's SHA-256, which produces a very long output and is much more secure than SHA-1. Okay, the relationship between hash and digital signature algorithms. So signature generation, you have a message, goes to SHA-1, produces a message digest. Here you have the private key, the DSA sign operation, the key into the public signature, you get the signature verification. The received message, SHA-1, produces the message digest, and then we decrypt that. The DSA verify operation is to decrypt that particular signature, and if it's yes, the signature is verified, or no, it's failed. The thing is, how do you create a digital signature from a hash? Output from MD5 or SHA hash provides input for an asymmetric key algorithm that uses a private key as input. The result of this encryption is a value that is uniquely associated with the file. It is computationally infeasible to forge and provably related to the identity of the entity that signs the file. Digital signatures and non-repudiation. A digital signature is an image of physical signature stored in a digital format. A digital signature is a combination of a strong hash of a message which acts as a fingerprint. Conditions for proving non-repudiation. You have to have an effective asymmetric key algorithm. It cannot be symmetric. You have to have a strong hash function, not MD5, something a lot stronger, maybe SHA-256. A means to apply the private encryption key to the hash value to produce the digital signature. A tamper-proof or trusted third-party timing device. An agreed-upon protocol for validating digital signatures. A secure key management and distribution system. A public key repository with an assured level of integrity. Key escrow to be able to produce public keys from reluctant parties. And procedures to handle disputes. Principles of key certificates and key management. The best key management system in the world does not protect against a brilliant cryptanalyst if the encryption algorithm itself has any weaknesses. Some modern key management techniques. Again, we talked about the Advanced Encryption Standard, Internet Protocol Security, IPsec, the Internet Security Association Key Management Protocol, ISA-KMP, the Extensible Markup Language, XML Key Management Specification, XKMS, Managed Public Key Infrastructure, PKI, and the American National Standards Institute, ANSI, and their X9.17. So in summary, we talked about the basics of cryptography, business applications of cryptography, symmetric and asymmetric key cryptography, encryption mechanisms and techniques, and certificate and key management, and this concludes Chapter 9.